All right, so we'll get started. So again, this is the last call for homework number 10. That's due tonight, okay? And the next two assignments are also online. All right, for the classroom disinfection, I'm asking Connor and Isaac for today. Okay. So we'll be starting volume 3 of university physics from today, and then we'll be checking just a few chapters here. I don't think we have time to go through each sections of so in this volume we'll be going over chapter 1 to 4, but we will not be going each individual sections of all these 4 chapters. Okay, so we'll just go selectively on the sections. All right, so these 4 chapters are on optics, and then most of the time you'll be use your geometry and trigonometry knowledges intensively on these 4 sections, 4 chapters. Okay, all right. So that's with the start with chapter 1, the nature of light. Okay. Let's see. So it has been it was like in the 19th centuries, people have been starting to look to measure the speed of light. And the first attempt was, or this is the one of the first attempts, to measure the light, speed of light by observing the period of the satellite of Jupiter. Okay, so you can measure the time and at 2 locations. So light travel from the satellite over there um, to the Earth over here. So if that's 1 period, then the Earth will travel from here to there. And you can also measure that period. So Earth will go from here to here. So on this side, Earth is going away from the satellite of Jupiter. And then here, Earth is going towards that. So using that differences for the distance and the time, you can calculate what's the speed of light. That was the idea, okay? It wasn't too bad. So it was estimated to be speed of light to be 2.0 times 10 to the 8th, okay, meters per second, which we know by now is about 3 times 10 to the 8th. So, but that wasn't too bad, okay? So it's 33% off, but it's still at the same order of magnitude, okay? So later on, there's improvement on the measurement of the speed of light. So this is one of the setup that in the early days people used to measure speed of light. So basically, you have a light source over here, gives out light, will hit on this semi-transparent mirror. So half of the light will be reflected, half will go through, okay? And when that happens, then the reflect beam will be going in this direction and then hits another, going through 2 lenses, hit another mirror over here. So these 2 lenses are basically focusing lenses, okay? And there's this guy here, rotating teeth wheel over here. So you can tune the speed of the teeth. So then when the light first pass through over here, when it comes back here, it will then, this will be moved by a distance like a teeth. Okay, so then it will pass through the second teeth over here. All right. Otherwise, if you don't have the correct speed for this rotating wheel, then you will block the light. Okay, you will not see it from the observer, the detector. Okay. So the path will be placed in like several kilometers, and then you can time the time. So you are measuring the time it takes to go from the light source and then reflect back to the detector here, and then divide by the time, or the distance you already know, and then divide by the time. So at that time, it was estimated to be 3.15, which is pretty good compared to the theoretical value, okay, 10 to the 8th, okay. And then later on, there was a further improvement of the setup so that you can actually estimate the speed of light to be 2.98, okay, times 10 to the 5th. So this guy is about 5% off, overestimated. And then this is about, it's less than 1% or less than 1,000th of difference to the real speed of light. Okay, so speed of light. This is from the Maxwell's equation. You can calculate it theoretically in vacuum will be the speed of light. Okay, so it's this number, exact number, 299,792,458 meters. Okay, and that's how like the standard of meter is being chosen today. Okay, so you are using basically 1 over this number of the speed of light to be 1 meter. Okay. Um, for the speed of light, when objects moving at less speed, and so then we use a distance called light year. Okay, especially in astronomy when the distance are very large. So 1 light year is measure of distance. It's not year. It's not measure of time. Okay, so it's the speed of light times the seconds in 1 year that gives you the distance. Okay, travel for the light. Okay, to be 9.46 times 10 to the 15 meters. And so we'll pretty much just use 3 times 10 to the 8th meters per second. Okay, so for estimation for the speed of light. Now, speed of light of the light is travel in medium actually slower than it travels in vacuum. So it depends on what medium you have. So this is pretty much referring to transparent media because light will not transport in non-transparent medium. Okay, so then if you do the speed of light in vacuum divided by the speed of light in medium, that gives you the index of refraction. Okay, so this is the index of refraction, which is the factor that the speed of light in vacuum is being reduced. Okay, when it enters the medium. Here's a table of the index of refraction for light going through different medias. So for solid, transparent solid, you can see that those are the numbers. Liquids, okay, these are numbers. So you might want to memorize that the water because that's the one thing that will refer to it very often. So for water, index of refraction for light is 1.33. And then also for speed, index of refraction for air is 1.000. So 3 zeros after decimal point 293. Okay. And a lot of times you can just use 1. That is the same as the index of refraction in vacuum. Okay. So speed of light in air is not reduced by much compared to the speed of light in vacuum. Also, for other gases, it's pretty much the same. Okay, it's very similar. For if you have a gas of carbon dioxide, it's again 1.0000, 4 or 3 zeros after decimal point and 45. Okay. All right. So to describe the how light travels, we use ray models. So that means if a light travels from one object to another, one place to another, then you are just using a straight line with an arrow if this is through the media. Okay. Now when it hits the interface of media, then the direction will change. Otherwise, in the same media, it will be a straight line. Okay. All right. So for this chapter, we'll pretty much just focus on geometric optics. That means you'll use optics geometry a lot. Okay. All right. So let's take a look on here. So this is again the when the light from sun hit the earth in between in the vacuum is straight, just travel straight forward. Okay. And then when it hit atmosphere, then it will be deflected because the index of refraction of vacuum and atmosphere is different. Okay. And when it hits object, it will be reflected. Okay. So if there's a mirror over there, you can see it will be reflected. Okay. All right. So the first thing we'll be looking at here for light to interact with medium. So this is when light hits on a surface. Okay. So when that happens, then you will have reflection of light. So it will be reflected. Okay. We will define the instance angle as the direction of the ray hitting on the surface with the normal direction of the surface. Okay, so that's theta I, theta instance. And then the reflected angle also, this is the angle between the normal of the surface with the reflected ray, okay, coming out of it. So these two should be the same. Theta I should be equal to theta R. Okay, so that's the law of reflection. We have, I think we have studied this in lab already. Okay. Now depends on the smoothness of your surface. If your surface is very, very smooth, okay, then if you have parallel rays coming in, hits on the surface, they will be reflected in the same direction, okay, because the normal direction at each point is the same, okay. However, if your surface is rough, okay, something like this, then at different point, when the rays hit the surface, the normal direction is different. So then reflected ray will be scattered in all directions, okay. If you have a smooth surface, it's called specular reflection. If you have a rough surface, it's called diffuse reflection, okay. All right, you might think that diffuse refraction is bad, but it's not always the case, right? But because, for example, when you are driving in the dark, in the night, you need diffuse refraction for the reflected ray to come back to you. Then you can see the road surface. Otherwise, if your headlights hits on the surface and reflect over there, no light, no rays come back to you, you will not know what's going on the road surface, okay? So it's not always bad. All right. And in this case, you can see, so if you have specular reflection, then you can only see the surface at certain angle when the light is reflected. Okay, so if you are over here, then you don't see any lights coming into your eye, you will not know the condition of the surface. And then on the other hand, this is diffuse refraction, so you can see pretty much the surface on any angles. Okay. All right. So let's take a look on specular reflection. So when I suppose like every one of us have looked at the mirror this morning when we got up. Okay, so you'll see your image in the mirror. Okay, so for the image, for the mirror image, or this is the image formed by specular reflection. So you'll see the image behind the mirror. All right. And then the size of the image and the object is the same size. Okay, so this you can actually apply the law of refraction to see that. So you can pick up a point like the head and the foot over there. So you'll see when the light from the head hits the mirror, get reflected back to your eye, you'll see where it is. Okay, behind the mirror. Okay, you can back extend that. And then also like a foot over here, you can see the foot hits here, reflect there. So your image appears to be coming from here. Okay, so you can see where that is. All right, so the image formed by a mirror, a plane mirror, okay, in this case, there are several properties of the image. So the first, the image is upright and it appears reversed right to left. So if you raise your right hand, your image will raise the left hand, as you can see, and then the other way around, okay? The mirror image appears to be the same distance behind the mirror that the object is in front of mirror. And also the mirror image is the same size as the object, okay? So this refers to two prime mirrors. If you have curved mirrors, then the image properties are different, okay? All right, so we'll take a look on one example here. So this one says you stand 1.5 meters in front of a wall and gaze down at a small vertical mirror mounted on it. in this mirror, you can see the reflection of your shoes if your eyes are 1.85 meters above your feet. Through what angle should the mirror be tilted for you to see your eyes reflected in the mirror? Okay. So for geometric optics, you pretty much for each problem, you want to sketch the problem and then to see the geometry, okay? So we'll do it that way here. So let's say there's this wall here, and then there's this small mirror mounted on the wall. You are standing 1.5 meters away from the wall. Say this is you standing over here. So this is your shoes. So the way you can see your shoe in the mirror is light comes off your shoes, hit the mirror, and get reflected. That reflected light will hit your eye. That's how you see it, okay? So this angle, this should be your theta I, this should be your theta R. They should equal to each other according to law of reflection. And you can back extend here to see where your image is at. So it should be the same 1.5 meters and the same size. Okay. All right. Now, in this case, because this mirror is very small, okay, so you can see then if the image of eye would be somewhere here, right? So if the light comes off from your eye, one of your eyes, then hit the mirror, will be reflected over here, okay? So you can only see the eye from somewhere here if this is the how the mirror is being mounted, okay? So you want to turn this mirror so then the light coming from the eye here hit the mirror will come back to the eye, okay? So you want to tilt your mirror in certain direction, all right? So then when it hits there, it comes right back. So that means in that case, your instance angle and reflected angle are 0, right? They are along the normal direction to be go right back, okay? So we are looking for how much angle you should tilt. So then it's basically asking you what would be this angle that you need to tilt from. This is original normal direction. Now you want to tilt it into that direction. So we are basically looking for this angle, okay, on the angle, right? So that's the problem here. It tells you that this distance is 1.5. It tells you from the eye to the foot is 1.85 meter, okay? So it looks like we have the geometry here set up. So this should be, because this angle is equal to this angle, so this should be half, okay? Half of the 1.5, so 1.85. So this would be half of that. And then this is 1.5. So you have this theta r you're looking for, you can do tangent of theta, right? So it should be this one over that one. So in that case, tangent of theta r is equal to 1.85 meters over 2 divided by 1.5 meters, right? Then you can solve for your theta r. Will be tangent inverse of 1.85 meters over 2 times 1.5 meters, okay? So as you can see, when you sketch the problem, then this is purely geometry here. So this would be equal to 31.7 degrees. Okay. So that's how much you want to tilt your mirror. Okay, so in that direction, just tilt towards that direction in order to see the eye in this small mirror. Oops. Let's see. All right. Let me know if you have any questions on this one. Okay, so if we are clear, we will move on to check on. So if you have two mirrors perpendicular to each other, so then that makes a corner reflector. So in this case, if the light comes through here, then it will be reflected backward. So these two will be parallel to each other. Okay. So this is called a retro refractor because then light hits in will come back parallel to it. Okay. And you can see this from geometry. If it hits here, this angle should equal to that angle, all right? And then this will hit there. So then this angle equals to that angle. Okay. So in the sense, this is the normal line. This is perpendicular to each other. So this is parallel to that. So this angle will be equal to this angle. Okay. And this angle will be equal to the angle. So that means this angle is equal to this angle. This two are parallel to each other. So this is parallel to that. Okay. So that's just purely geometry. If you have three mirrors perpendicular to each other placed in the corner of the wall, then you'll see the same thing here. It will be reflect backward in that direction. Okay. All right. So that's on the law of refraction. Now, next, let's see when the light hits a surface and then transmit into the surface. Okay, so when a light hits a surface, actually part of it will be reflected, and then part of it will go into the medium if the medium is transparent. Okay, so then this is what happens. So this is a top view of it, of this figure. So there's just one fish there, but because the light coming off from the fish hits the walls and then get refracted to the eye here. So it appears you are seeing like 3 fishes there in the tank. Okay. So let's take a look on that. When the lights hit the median, the interface of the two medians, so then part of it will be entering the second median, and then part of it will be reflected. So we have talked about that. So we are going to just ignore that part, but just focus on the refraction here. In that case, this is governed by Snell's law. So N1, index of refraction for median 1 times sine of theta 1, that's the incidence angle, equal to N2 times sine of theta 2. Okay. And so if the light goes in the opposite way around, so that still applies. Okay, so it doesn't matter which way light is going. Okay, so as long as you have the normal correct here, then theta 1, theta 2. Okay. Now, because of the index of refraction is defined as V equal to C over N, so you can rewrite, so N will be equal to C over V, right? So then take that into Snell's law. It says N, so N1 sine theta 1 equal to N2 sine theta 2. So N1 will be equal to C over V1, right? And then N2 will be equal to C over V2. So the C will cancel out. So then you can also write the Snell's law as sine theta 1 divided by V1, which is the speed of light in median 1, equals to sine of theta 2 divided by V2, the speed of light in median, in the second median. Okay. So that's the result of combining Snell's law with the definition of index of refraction. All right. So when you have, if you have refraction, so these are the properties. So when a ray of light enters a median where its speed decreases, then it's bent towards the normal direction. Okay, so that's we can go back a couple of slides here. So if this is air, this is water. Okay, so let's assume that's the case here. When the light travels in the air, that's the same, similar about the same speed as the light travel in the vacuum. When it enters the water, the speed decreases, right? So you are entering from a larger speed of light into a media has a small speed of light. So then it will bend. So this guy will bend towards the normal. Okay, so that's that direction. Now in the other way around, if you are coming from the light ray coming from the smaller speed to a larger speed, then it's bent away from the normal direction. So if you go this way, then it's bent towards that, away from the normal direction. So that's basically the first two here. All right. The third one says there's no change in direction of propagation if there's no change in index of refraction. Okay, so that pretty much means if the index of refraction doesn't change, then the light is going to go through a straight line. So if you have the light going in just in vacuum, it will travel in straight line, or in the same medium that does not have change in index of refraction. Okay. All right, and then the next one says the greater the change in index of refraction, the greater the change in propagation direction. Okay, so that basically says the diffraction will be more if the change in index of refraction of two median, okay, is larger. All right, the last one here says if a ray of light goes from one median to another along the normal, it's undeflected regardless of the index of refraction. Okay, so if you have light just hit on the normal direction, then theta I is equal to 0. So then the theta or theta 1 is equal to 0. Then theta 2 will be equal to 0 too, because n1 and n2 are not equal to 0. Okay, according to Snell's law. All right. So in real life experience, you probably see this if you put maybe a straw in your drink, then you'll see it feels like the straw is bended. Okay, so similar, if you put a pencil in water, you'll see that. Okay, as well. Now, in a hot day in the summer, okay, when you look down on the road ahead, you'll see images of the surroundings there. So that's because during a hot day, the surface of the road is hotter than certain distance above the surface. So then the index of reflection of air actually has gradient. It actually changes, okay, along the direction because here is hotter, here is cooler. So then the density of air varies, okay. So then the light from the tree will be bended in the air and then gets into your eye. So you feel like, so when you see the light into your eye, you'll just, it feels like it's coming from somewhere down here. Okay. So that's why in a summer, like summer, pretty much summer days, you'll see the images of the surroundings on the road ahead of you. Okay. All right. Let's take a look on the example on the Snail's law here. So this one says a submerged scuba diver looks up towards the calm surface of a freshwater lake and notes that the sun appears to be 35 degrees from the vertical. The diver's friend is standing on the shore of the lake. At what angle above the horizon does the friend see the sun? Use the index of refraction 1.33 for fresh air, and then by default you can use 1 as index of refraction in air. Okay. So again, let's sketch the problem here. See what's going on. So let's assume the surface of the lake is very calm, so it's kind of flat. Okay, so scuba diver is under the water somewhere, and then I'm just going to just draw one eye of the diver. Okay, so the normal direction of the surface is the vertical direction. So the sunlight, sun somewhere here in the sky will have the ray hits the surface here and then get deflected. I don't think I have. So let me just draw the eye of diver somewhere here. Okay. All right. So enters the water, the ray enters the water and then hit the eye on the diver here. It says this angle is 35 degrees because then to the diver it appears somewhere here. Right. Right. So this is the theta 2. Let's call this theta 2. And this will be theta 1. And of water, let me call it N2. This is 1.33. Index of reflection for the air, we can just use 1.00. Okay. Now, asking you if a friend somewhere here, let's say somewhere here. So if you are, so sunlight comes in pretty much like parallel to each other, right? So you just have to imagine this is a very large sun, so it goes has rays parallel to each other. So a friend somewhere here will look up So this will be the direction. Now it's asking for this angle, right? So the angle the ray comes in make with the horizon. Okay, so that's the angle we are looking for. So you can calculate this by theta 1, the instance angle, and then because instance angle plus this angle is equal to 90 degrees, so we can calculate for that. Okay, so pretty much you are applying Snell's law n1 sine theta 1 equal to n2 sine theta 2, and theta 2 is given. So theta 1 will be equal to sine inverse of n2 sine theta 2 over n1. Okay. N2 is 1.33 sine of 35 degrees divided by 1.00. That gives you pretty much roughly, or 49, sorry, 49.9 degrees for theta 1. Okay. Then the angle theta you're looking for is 90 degrees minus that. So it'll be about 40 degrees. All right. Okay. So let's move on. If you guys are clear with this. So you can imagine there's a special case for if you have the light go from the denser media to a thinner one. So let's take a look on this guy. So if this is water, this is air. So when it hits here, so as I mentioned, part of it will be reflected, part of it will be refracted. Okay. So for the refracted ray over here, because media 2 above here is thinner, so then it will be reflected. This theta 2 angle will be greater than theta 1 according to Snell's law. Okay. So if you have n2 greater than n1 or n2 smaller than n1, then theta 2 is greater than theta 1. Okay. So as you can see here, theta 2 is greater than theta 1. Now as you increase your theta 1, theta 2 is going to be further increased. Okay. So theta 2 will reach 90 degrees first because theta 2 will be greater than theta 1. All right. So after that happens, now if you keep increase the instance angle, then the light will not enter the second media. Okay, it will be reflected totally. Okay, so when the instance angle is greater than that critical angle, when theta 2 is equal to 90 degrees. Okay, you can calculate if you are given the index of refractions of the two n1 and n2, what would be the instance angle theta 1. Okay, so when that happens, theta 2 equal to 90 degree, sine of 90 is 1. So then n1 sine theta 1 is equal to n2. So you can calculate this theta 1, which we call a critical angle of theta c. That should be sine inverse of n2 divided by n1. Okay. In the case of n2 is less than n1 or n1 is greater than n2. Okay. All right. So that's what's going to happen if your instance angle is greater than your critical angle, totally be reflected. This is called total internal reflection. Okay. All right. So let's take a look on the example on total internal reflection. So this one says you can determine the index of refraction of a substance by determining its critical angle. What's the index of refraction of substance that has critical angle of 68.4? degrees when submerged in water. And what's the substance based on table 1.1? So there's a table 1.1 lists the index of refraction for each materials. What would the critical angle for this substance in air? Okay, so again, let's sketch the problem here and then see what is this talking about. So you have water. So let's say this is water. You have this material submerged into water. So that means just say this is a rectangular materials over here. Now it tells you the critical angle of this guy is 68.4. So that means when the incidence angle from this median is equal to 68, so this is 68.4 degrees, then total internal refraction happens. Okay. So then this is equal to 90 degrees. So in that case, this is theta 1, and the 90 degree is the theta 2. N2 is the water 1.33, okay? And then N of this material, let's call it N1. So then you would have find Snell's law N1 times theta 1 equal to N2, right? Basically N2 of 90, sine of 90 degrees, so that's 1, so just N2. So you can calculate what's your N1. That will be equal to then N2 divided by sine of theta 1. N2 is 1.33 divided by sine of 68.4 degrees. Okay. So that will give you 1.434 for the index of refraction of this material. And we can go back a few slides here to see what will be the materials. So index of refraction, so it looks like it's going to be, actually it's not listed here, but if you look at in the textbook table 1.1, so let's see about that. So you can go to your textbook volume 3. You can search table 1.1. Not responding. This is the table 1.1. So 1.434, this is what we got. Okay, so this is the fluoride. Yeah, we got 1.434. That's that guy there. Okay, so you can look it up and then you can identify that it's going to be fluoride for the substance. Okay. This one. Okay. All right. Now part B is asking you what would be the critical angle for this substance in air. So then the second part you will be putting this thing in air. So if it's air, um, so then N2 will be the index of refraction for air. You can use 1.00. Okay, and for N1 of the substance, we have it already determined in part A. So then we are looking for what's the critical angle. So for critical angle, you will be using N1 sine theta 1 equals to N2 um, sine of 90. So that would be 1. Okay, so we are solving for this now. Will be equal to N2 over N1, 1.00 divided by 1.4. Actually, let me see. No, yes, that's right. So N1 is like 1.434. So then theta 1 would be sine inverse of 1.00 over 1.434. Okay, that would be your new critical angle, which we can say sine of critical angle, okay, in that case. So this would be equal to 44.2 degrees for the critical angle. All right. All right. So I think this chapter is getting much easier than the previous chapters. Okay, so um, I'm assuming you guys are clear with it, but just in case, okay, if you have any questions, you can just let me know. Okay. All right. Um, so there's several very useful applications for total internal reflection. So when that happens, you don't lose any intensity of your light. Okay, so for fiber optics, so that's basically when the signal comes in. So for light signal or for EM waves comes in, it will be having total internal refraction when it hits the wall of the the fiber optics. So then the signal is 100% preserved when it goes through the fiber optics. Okay. Also for binoculars, there's several pieces that will have the total internal refraction for the ray. So then you keep the intensity 100% when that happens. Okay. All right. Next, let's take a look on dispersion. So if you see rainbow, so that's because the sunlight is made of actually different colors. Okay, so then all the colors blend together to give you white light. Okay, in that case. However, um, when there's air drops in or the water drops in air, then different lights will be reflect at different angles. So basically, the light will have different index of refraction according to their frequencies. So if you have different frequencies, even though they are entering the same material, their index of refraction will change slightly, okay, from one to another. So this is what happens. So for instance, white beam comes here. So if this is pure light, a certain like wavelength, a certain color, say maybe blue color goes in, then just goes out. Okay, so if you have white light, it's a mixture of all different colors. So because of the wavelength is different for different colors, their frequencies are different. So then when they are deflected, um, they will be deflected at different angles. Okay, so for different lights to be um, deflected at different angle on the other side of the prism, we call this as dispersion. Okay, so you can use a prism to just spread out different colors. All right, so we'll take a look this one here. So this is the index of refraction for red light in a certain liquid. So it's 1.305, but for violet light, it's 1.336. Okay, so they are different slightly. Find the dispersion of V theta V violet minus theta R for red and violet light when both are instanced from air onto a flat surface of liquid at the angle of 45 degrees to the normal. Okay, so let's take a look here. So let's call this as the below this line is the material which has N2. Okay, for red light, so I'm going to say index of refraction of for red light is a 1.305, and then index of refraction for the violet into V is 1.336. For N1, you can assume they are the same because they'll be about 1.0003-ish after decimal point. So you can just pretty much treat them as the same. So this is the normal direction. Let's just pretend that the blue color is the violet, and then the red one also comes in at that angle. Okay? So the two comes at the same angle of 45 degrees with respect to the normal. So then when they enter the median, for the red light, it's going to be deflected. And then for the violet, it's going to be deflected in a different angle, slightly different angle. Okay? So this is theta of R, and this angle will be theta of V. And you're looking for theta V minus theta R, dispersion of two angles, two lights. Okay, that's what you're looking for. So you apply Snell's law to the red light. So you'll do N1 sine theta 1 equals to N2 red sine theta red. Okay, then you can solve for your theta R, and then you'll do the same for the violet. N1 sine theta 1 equals to N2V sine theta V. You solve for theta V there. Okay, so 1.0003 if you want, or you can just use 1.00. That should be fine too. Sine of 45 degrees equal to N2 of R 1.305 sine of theta R. Okay, so for that, your theta R is going to be 32.8093 degrees. The same here, you can solve for your theta V 1.0003 sine of 45 equals to 1.336 sine of theta V. Okay, so your theta V is 31.9562 degrees. Okay, so in this case, you can see you want to keep extra digits because the difference are small. So then the difference of the two, theta V minus theta R, is equal to 31.9562 minus 32.8093. Okay, it's about 0.8531 degrees. Okay, I'm not sure. You might be asked to find the dispersion of two lights for when it hits the prism. So you might have two lights coming here, maybe a red, violet. Maybe I think they are coming at the same angle. Okay. So then you apply Snell's law over here one time. That's what we did for both of them. Then they will be deflected at different angles, probably. And then you apply Snell's law the second time when they hit this surface for the second time. Okay. Then you'll be looking for the difference of the two angles in that case. Okay. I think you have one question in the homework assignment on that. All right. So let me know if you have any questions. Right. So then quickly, so when you see rainbow, that's because there's air drops or the raindrops in air, water drops. So the sunlight, the white light comes here, hits the surface of the raindrop here one time, get reflected. Okay, so if you look at two lights there, you'll see they are coming into the water drop at different angles, and then they will be reflected and then get refracted at second time. So when the two come out, they are at different angles. Okay. So and then if you have all the colors, you can see they will be dispersed at different angles. That's how you see the rainbow. Okay. So when you see the rainbow, it's pretty much around 40 or 42 degrees in that range. Okay, because of that. If you see double rainbows, in some cases, that's because then the first primary rainbow is for the sunlight to hit this guy, refract it, and then reflect it, and then refract again. But for the secondary rainbow is less intense. So you'll see it's actually get reflected twice, okay, in over there, okay. And that's an angle about 51 degrees, okay. So that's the secondary rainbow. Sometimes you see this rings because there's icicles or ice crystals in the air, okay, and then you'll be seeing these two brighter ones. Those are called sundogs. They're also because there's ice crystals, okay. All right, so I think we'll stop here for today.